Hello. So welcome everyone. Yeah. So my name is Yogesh, and I work as a cybersecurity analyst at TCS Cybersecurity Unit India, where I spend a lot of time working on IoT and mobile application security. Apart from that, I love to build and play with robots, and sometimes break them very often. And today I'm here to talk about the security in Bluetooth low energy devices and how to hack the fitness trackers. So let me tell you a story. It all began a year and a half back when I started getting excited about IoT security. It's just that I saw many people having IoT devices at their home. IoT was just booming up. So as a security guy, I had to focus on IoT. And then I realized I needed a device. So I got myself a fitness tracker, definitely not to stay fit, but to hack it. So once I got the fitness tracker, I started researching more and more about how does it connect to the mobile application and what are the communication protocol that it uses to interact with the mobile application. And then I realized there was a communication protocol called BLE. Far more less different than your Bluetooth Classic, but pretty much almost same. So it uses BLE protocol to communicate with your mobile application. And then I started realizing that I could do something really cool with that. So, and then I started hunting for, box in that fitness tracker. And then I found something really cool. So this talk will be on how I found the vulnerability in the fitness trackers and how I was able to hack into the fitness trackers. So expectations. So what can you expect from this talk? You'll be getting basic understanding of Bluetooth. And then I'll talk about what exactly is the difference between Bluetooth Classic and Bluetooth Low Energy. And then after that, I'll be talking about the BLE stack and what we generally call Bluetooth man in the middle attack, which is capturing the BLE packet. So whatever conversation that you have between your mobile application and your fitness tracker. So I'll be talking about how to capture them and what hardware or what software you need them. And then after that, I have reverse engineering the mobile application of fitness trackers. It could be anything. A lot of time what happens is in these so-called smart devices, they have that on mobile application. And then these hardware manufacturers forgotten to harden the security, forgot to harden the reverse engineering process. So what happens is a lot of information could be gathered from here. So I'll tell you how exactly to reverse engineer the mobile applications. And at the end, I'll be talking about how to upload the firmware over the year. This is something really cool. So if you want to upload the firmware over the year in the BLE devices, I'll be talking about how exactly to do them. So all right, first let's talk about Bluetooth. Bluetooth is a short-range wireless communication protocol and allows devices such as your smartphones, headset, and many other smart bulbs, etc. to connect with each other and share the data and a voice wirelessly. It was developed in 1994 by Ericsson as a replacement for cables and uses 2.4 gigahertz frequency and creates a 10-meter radius called Piconet. And for many years, what happened was it had constant data transmission. That just means high power consumption, right? When you have constant data transmission in the device, it has high power consumption. When it has high power consumption, this Bluetooth application suffered a lame battery life for many years. Until a few years ago, Bluetooth 4.0, or what we can generally call Bluetooth Smart, came into the scene. It's basically the power efficient version of Bluetooth that has made many amazing devices possible, like your fitness trackers, your coffee makers, your light bulbs, and many medical devices, etc. If you see the applications of BLE devices, it's right now everywhere. This version of Bluetooth Smart, or simply called BLE, is designed to be power efficient and low cost. And that's the reason why you can get these BLE devices for as low as $7 to $8. You can get any BLE applications for $7 to $8. But yes, BLE is an awesome technology. It enables us to connect to everyday things that we thought wouldn't be possible to do. Have you ever thought that we would be any day connecting the smart shoes with your with your mobile application? Not right. So right now, thanks to BLE, smart shoes are out there in the wild, and you could count how many steps that you walked, and you could do so much things with your smart shoes, right? So now let's talk about what exactly is the difference between the Bluetooth Classic and BLE. So this Bluetooth Classic is generally what you see in your in your headset, in your Bluetooth speakers, and BLE is what you generally see in the smart devices. So this Bluetooth Classic is great for product that requires the continuous streaming of data. Your headphone has the continuous streaming of data, right? Your Bluetooth speaker has the continuous streaming of data. So in those applications, Bluetooth Classic is always preferred. So when it has it has continuous streaming of data, it has higher power consumption and needs to have a faster data rate as well. But on the other hand, I have this Bluetooth Low Energy. This Bluetooth Low Energy is great for product that not require the continuous streaming of data, like maybe in your smart bulb, just to send on or off to the bulb, right? So in that case, you don't need the device to continuously send on, right? You don't have to send that. So in that case, we prefer BLE over Bluetooth Classic, and it has an ultra low power consumption. Since it doesn't have to do the continuous data transmission, it can go for slow data rate as well. The beauty of BLE is that it is designed to operate in the sleep mode and waken up only when the connection is initiated. So what happens is, you have a Bluetooth low energy device, maybe a smart bulb. The connection between your central server, that is a mobile application, and the Bluetooth application, the connection is on sleep mode when there is nothing to send. So it is waken up only when the connection is initiated. That's the reason why you have fitness trackers that can go on and on for days and days. The battery life can go on and on for days and days, right? And this is best suited for your home automation, fitness trackers, and many other things. But being said that, it is not perfect. It has flaws. Almost at any point in time, it's discoverable. It's like, hey, I'm here, send me any information and I'm going to spit out. Send me anything and I'm going to spit out the information. It works on the same frequency and same channel always. There is no channel hopping. So if you want to do a denial of service attack, it can happen because there is no channel hopping here. And almost at any point in time, it allows any device to connect to it. And on top of that, most of the devices do not take the benefit of link layer security, link layer encryption. So what happens is, if they implement this link layer encryption, the cost of the devices are going to go up high, but they have to sell a lot of them, right? So these hardware manufacturers blindly do not, has this link layer encryption. But there are few devices like your smartwatches; those are costly, that can go for $200 and up. That really has the link layer encryption. You can capture the packets in between. You can perform the man-in-the-middle attack, but the packets are encrypted. Yes, you can decrypt the packets also. So now let's go back to the fitness tracker that I talked earlier. I decided to focus on the fitness tracker is because I saw many people using that, and I decided it would be really fun to pop up some notifications, pop up some messages on my friends' fitness trackers. And to do that, we need to understand this BLE stack. So in BLE, this is the BLE stack. So in BLE stack, there are two really important that you need to remember. That is generic attribute profile and generic access profile. So the first thing, GAT. GAT defines the way these BLE devices communicate with each other, the client and the server. The client could be your fitness tracker and the server could be a mobile application. Using something called service and characteristics. Remember this term service and characteristics? I'm going to use it very often, and I'll tell you what exactly is that. So here, connections are exclusive in BLE. The connections are exclusive. When I say exclusive, it's suppose when the client, that means a BLE device, is connected to one central server at a time, it won't advertise itself, saying that, hey, I'm here. So once it is connected, it goes into the, it stops advertising itself. So no any other device can be connected until the connection is actually broken. So now here in BLE we have something called profile. Profile is actually, it doesn't actually exist in a BLE, but it's just a collection of service and characteristics. Service defines, it's a set of provided features associated with the associated behavior to interact with the peripheral. Each service has one collection of characteristics. Characteristics are defined attribute types that contains a single logical value. Now, example, in your fitness tracker, service could be something like device information. Device information is a service, and characteristic could be something like software revision number, hardware revision number, or maybe any value, and maybe your hardware name or something like that, right? So now, this is an app that is there in the Play Store. If you want to install, I'll talk about this app on the later slides. This is an app called NRF Connect, which allows you to scan the nearby BLE devices. So if you see here, there is something called device information down there, which has a UUID as well. So the device information is actually a service. Inside that, if you if you open up that, you would see software revision number, hardware revision number, and the device name itself. So this is the actual definition of service and characteristics. So what happens is, if you really wanted to attack a BLE device, there are a few basic processes. The first is step number 0, selecting the target. So here what happens is, you would want to collect more and more information about the device. It's always better to actually refer the hardware manufacturer's manual. There is nothing as better than a hardware manufacturer's manual to grab more and more information about the devices, right? And in Linux, if you are in Linux, there are many tools like BlueZ Stack, HA tool, and GAT tool, which allows you to gather more and more information about the devices. And the step number 1, once you have all the information about the device, now you're good to go. So now you want to enumerate the service and characteristics. You want to figure out how many services are running in that particular one, and how many characteristics are running there. And you want to figure out what service does exactly what and what characteristic does exactly what. The basic process is you could use the tools like HCA tool to scan the nearby devices, and then connect using something called GAT tool, and then you can list down all the service and characteristics. Sometimes, most of the times, what happens is your characteristics are just unknown services. If you want to figure out what exactly characteristic is doing what, you could just do Google search. There you could find many information. And then step number 2, that's reverse engineering the mobile application if they have any. For reverse engineering, in Linux we have something called APK tool. Using that you could reverse engineer APK tool -D. They could decompile any Android applications. So what happens here is, like I was working on hacking a smart lock that you generally get. So I ordered it from somewhere from China, and once I got it, I reverse engineered the mobile application. The default password to unlock that lock. Suppose if you don't have the mobile phone with you, or maybe you want to physically unlock the lock, it had some hard-coded password. So once you reverse engineer the mobile application, the hard-coded password was there inside the mobile application. And many times, a lot of information, like figuring out how exactly your BLE application is connecting to your mobile application, every information that you need to connect between your mobile application and your BLE devices is there in the mobile applications. So if you're good at reverse engineering, this is a very good chance to start that. And then after, the last one is finally doing some cool stuff, maybe sending some notification, maybe changing the light bulbs, turning on and off your neighbor's light bulb, and many other things. And in the reverse engineering, I would be surprised if you didn't get any information, because all the devices that I had tested out had something at least in the mobile applications. So step number 0, that is selecting the target. This is the very first step that you want to do. You want to find out the nearby Bluetooth devices, right? So for that, if you are in Kali, any version of Linux distribution, you have something called BlueZ stack. So BlueZ it is as easy as installing sudo apt-get install BlueZ. So all the tools that I mentioned earlier, HCA tool and GAT tool, comes pre-installed with the BlueZ stack. So you can download the BlueZ stack. Once you download the BlueZ stack, you can see the command there, sudo HCA tool and lay scan. Lay scan means low energy scan. So you can scan all the low energy devices near your vicinity. And then, so if you wanted to do, if you're on Android and you want to do it from your Android mobile phone, you can download this mobile app called NRF Connect. So it allows you to scan the nearby devices using a mobile smartphone. So you can just go to the Google Play Store and download this app. And if you're on iOS, you can download this Light Blue. iOS has NRF Connect as well as Light Blue. You can choose either of them. If your device is actually advertising, if it is not connected to any central server, if it is not in a sleep mode, it should pop up here. So, so this is how exactly it works. HCA tool, if you see the HCA tool, it's listing out all the nearby devices. There is an AMA band, there is a fitness tracker, and the next here you can see all the BLE devices that I have near my vicinity, and there is a screenshot from the Light Blue. You have all the health monitor, all these sort of devices out there. So step number 0 is selecting the target. Step number 1 is enumerating the service and characteristics. Here we're trying to figure out what services does exactly what. You can do this actively as well as passively. If you want to do it actively, then you can connect the device to your phone, and you can use apps like I mentioned earlier, Light Blue and NRF Connect to do that. Once you're connected, it's just gonna tell what services are running exactly what. So if you go back here, I didn't have the slide anyways. So once you connected in your NRF Connect, all these characteristics and services are going to have that name, like the one earlier you saw, device information, right? So like that, you'll have notification service in the fitness trackers, notification service, messaging service, and many other services. Or maybe in the Linux, you can have this tool called HCA tool. Using HCA tool and Kali machine, or maybe any of your favorite distribution, you can connect using GAT tool. And if you're connected, you can list down all the primary characteristic services using a command called primary and characteristics. This is for HCA tool. So you must have the UUID and handle. If you remember in my earlier third slide, the device information had something called UUID, right? So if you wanted to send or receive any sensor value, if you wanted to send, read what exactly is happening on particular sensor, you need to have a UUID. So that UUID could be, you could get it from HCA tool as well as you could get it from NRF Connect. But if you want to do it passively, that means you want to snip somebody's connection. At the beginning of these devices, when they talk with each other, they're like, hey, I'm here and I have this many service and this many characteristics, and this service does this, and this characteristic does that. So what happens is, if you could sniff this communication between the BLE device and the central server using some sort of hardware like Ubuntu, you could know what service is doing exactly what. So if you really wanted to snip the BLE packets, Ubuntu is the perfect solution. It's like, yeah, Ubuntu is a perfect solution. It works both for classic and BLE. If you wanted to capture the classic, the one which I told, if you wanted to do it for your headset, if you want to do it for your speakers, it works for classic as well. And it runs on open source hardware and software both, and it costs somewhere around $100. If you don't want to spend $100, there are cheaper alternative for that. These really cheap sniffers, CC2540, which is cheaper but with limited configuration. It doesn't have the higher data rate as much as Ubuntu one. It costs somewhere around $50. So if you're wondering how to capture the packet down to the packet level, Ubuntu is the perfect solution. I prefer not to use any sniffers at all because sniffers do drop a lot of packets. So if you're somebody like me who doesn't want to spend any money on hardware, there is an alternative on Android phone. So what I do is every time there is an app available on Android called NRF Connect, which I told you. Do install that and let the app communicate with it. So if example, you have a BLE device and you have a its central application, mobile application, the fitness trackers mobile application. So what happens is as soon as you start communicating, they're both going to share a lot of information, right? So if you really wanted to see that, what you could do is you could go to your settings, developer option, and 5 times. So you can go to the settings and about and tap the build number 5 times, and you could enable this developer option. Once the developer option is enabled, you can enable this Bluetooth HCI snoop log. So HCI just means host control interface. It's going to log all the communication that is happening between your mobile application and the BLE. So once you get that, you can pull off the file using ADB commands. I hope you're aware of ADB. If you're not aware of ADB, it's Android debug breeze. So you can just connect your mobile app. If the developer option is enabled, you can debug using the ADB. So you can pull the file from SD card and BTS snoop underscore say.log. You could take that file to any packet analyzer, maybe in the Wireshark or anything. I prefer to use Wireshark. So once you have that in the Wireshark, you can analyze the packets. So here you could see under which protocol it is communicating, under which UUID it is sending, and what all values it is sending. You could see everything there. So super easy, right? So now what happens is, now you're connected. You might ask me the question, hey Yogesh, I'm connected to the device. Now what's next? So next step is authentication. The fun thing is, this is one of the metrics that I had. 3 of the 5 devices that I tested didn't have link line encryption. And then 2 of the 5 devices that I tested didn't even have the authentication. Like the one I was testing out was a smart bulb. So in that smart bulb, the hardware manufacturer thought it would be really fun and really cool to let your neighbor next door to allow your lights to be turned on and off. Since it's a smart bulb, right? They didn't have any authentication. So then your neighbor next door could actually install the app in his phone and could just turn on and off the light. It was that simple, no any authentication. So this is the same thing. If they implement these security measures, the cost of the devices are going to go up high, but they have to sell a lot of them, so they just ignore it. So after the authentication, so this was the thing that I was able to do. Now I was connected to the fitness tracker using my HCI tool and GAT tool. I wrote my own scripts, and then after that I needed to do some really cool stuff, right? So now you have to reverse engineer the packets. So once I was reverse engineering the packet, I got something like this. It was sending values 0301 4869 to one particular channel, 2 particular characteristics. So then I realized it's doing something really cool here. The first 1 byte, first 2 bytes are actually a notification type. So if you wanted to place a notification saying that, hey, Trump is calling you, maybe you could do, just send 03. Or maybe if you wanted to send somebody, hey, your email is there on the fitness tracker, you could just append 01. You could replace it with a 01. And maybe if it's a missed call, you could just do 04, something like that. And the next one is how many notifications you want to send. So if you want to flood the notification, fitness tracker with a notification, you could just replace that with the number of times you want to send the notification, maybe 99, like that. And the last bytes are for sending what you want. So like suppose if I'm sending hi, it's the hex value of SI. S is just 48 and I is just 69. So it's calculating hex value and then sending it over the particular characteristics. If you see the characteristics right now, it's 5F9B34FB. This is one particular characteristics where the notification is being sent. So how I knew this is because it's from the Wireshark. Once you pull that log.log file, you could take it in the fitness track. You could take it in the Wireshark and analyze this packet, and you would know that when there was actually a notification coming on your phone on this particular 34FB characteristics, there was some value that was being sent. So once you reverse engineer that, you could figure out it was that simple. So then this is one of the very simple snippet of the code and tool that I built to send the notification. If you're interested in looking this tool is there in the GitHub, github.com/Yogesh Ojha, spelled as YOGESS if you wanted to look into the tools. So this is an example what I did. So I'm writing the values to one of these services 34@B. So if I do that, this is exactly what is going to emulate the device. So it's going to further notification. So what I got after that was I was able to pop up on anybody's fitness tracker saying that Trump is calling you, or maybe whatever notification that I wanted to pop up. It was that simple. So the next thing that I wanted to do was doing something on the firmware. The real question was why was I interested in firmware? It's because I saw many people using fitness tracker, and I thought, why not scare somebody with these icons or maybe images on the fitness trackers. So let's first talk about what exactly is firmware. Firmware is a piece of software that runs on an embedded CPU, typically written on C, is compiled into binary, and that is loaded into your device using a programmer or wired connection. But the next question is, how do I get the firmware, right? One option could be reverse engineering the mobile application that I told earlier, if they have any, and look into the directorial asset. Inside the asset, they're going to have everything for you. It could be a firmware, it could be a resources and anything. Otherwise, capture the file during the DFU update. Now, these BLE devices, they have something called over the year updates, right? So, what happens is over the year, if you have something, if there is new update, it's gonna first make a call to some API, maybe x.y.com / maybe new firmware.fw or something like that. So if you capture the firmware during the DFU update, you could get the firmware. For me, so this is once I reverse engineer the mobile application, I think, yeah. So once I reverse engineer the mobile application, in the asset directory, this is what I got. .fw file, that is a firmware file, and .res file, that's a resource file. So firmware file, you could do a lot of things, maybe write on custom firmware for that. And for the resource, like all the images that you have on your fitness tracker, everything was there inside the res. So if you reverse engineer again both of these, you can use any tools like Ghidra, the recent one launched by NSA, or maybe your favorite hex editors, or maybe whatever you want. You can use either of these tools and then reverse engineer these firmwares, and again for the resources as well as. So once I got the firmware, and the hunt for the firmware update service actually started, because I had to upload. Now I have the firmware, I made changes to the firmware, I had to upload it to somewhere, right? So if you remember, I mentioned an powerful app called NRF Connect. This is one of the screenshots from there. So once I got the firmware, I was expecting it to have clear name, device firmware update, and then hey, upload the firmware here. But in reality, what happens is hardware manufacturers sometimes slightly to harden the reverse engineering process, they might have unknown services. So it's not really difficult. You could go to GitHub and probably search for this particular UUID to see what exactly this UUID is doing, or maybe just go to Google and search what exactly this UUID is doing, or maybe in the hardware manufacturer's specification manual, you could just go and look for this particular UUID, and they have some of the other information on that. So once I got this, once I found out that okay, this particular characteristics is actually accepting the firmware, I started uploading the firmware, and I was wondering, I have a file called .fw file. How do I upload the firmware over the year, right? Yeah. So the next thing was how to upload the firmware, right? So when I reverse engineered, again, same thing here, reverse engineering the packets in the Wireshark, it's as simple as that. So when I reverse engineered, I found out that it was sending 4 byte. Initially, it was sending 4 byte on this particular characteristical 1531. So the first byte it was sending x01 was initiating the firmware update service. It's saying, hey, now I'm ready to send the firmware to you, and this is how I send. It's using 01. And then with that, it appends the file size in 3 bytes. So if a file size is maybe 100 KB or maybe even 3-4 KBs, it will translate that into your the file size into the hex, and then it's going to append that with 01. It's going to send it to the characteristics number 1531. Once it's sent, it's gonna the fitness tracker is ready to accept the firmware, and on your fitness tracker it just says, hey, I'm ready to accept the firmware. So now for the resource, the difference between the firmware and resource is that firmware actually controls the hardware. Resource is something which you have maybe your images of that skull that I showed earlier. Maybe you have, when you receive a phone call, you have that phone call image in a fitness tracker, right? So that's actually resource. So for resource it's actually 5 bytes. It has to tell to the DFU firmware update service saying that, hey, I'm not sending the firmware, I'm sending the resource. So it's gonna append 0 to this particular byte at the end of the this particular packet, saying that, hey, it's not a firmware, it's a resource. So once I started uploading the firmware, and then I realized it was stuck in 99% every time, and it was never accepting the firmware. I spent a lot of time figuring out what exactly was happening. Then I realized there was something important called checksum. So let's see what exactly is checksum. So what is happening there was, once the firmware is being sent, it's waiting for checksum values. So what exactly is checksum? Checksum is a calculated value that is used to determine the integrity of the data during the transmission, so that the man-in-the-middle attack doesn't happen. Checksum serves as a unique identifier for the data that is being transmitted. If the data is changed, the checksum is changed as well, right? This makes it super easy to verify the integrity of the data over the year. So now, how to verify the integrity is that the sender, when it is sending the firmware, before even sending the firmware, it calculates some particular checksum. Now receiver, when it finishes receiving the firmware, it is waiting for something called checksum. Now the sender is going to send the particular checksum to the receiver, saying that, hey, this was the checksum that I sent to you. Does this match with you with a high degree of confidence? If the answer is yes, it's going to accept the firmware. If the answer is no, it is not going to accept the firmware. So if the firmware was modified over the year in between, if it was the one I told you earlier, like using the Ubuntu, if the packet were being modified over the year, it's not going to accept the firmware. So once it has high degree of confidence, it's going to accept the firmware. If the checksum matches, the firmware is straight accepted. BLE doesn't perform the error correction, but only can perform the error detection. Okay, so Bluetooth 5.0, that is the new version of Bluetooth, it has error correction as well. There are several types of checksum available, but this fitness tracker that I tested had CRC16. Yeah, so this is how exactly the checksum is being sent. Once you initiate the connections by sending the first 01 bytes and then the file size, the firmware is sent, and once you start sending 4 bytes at a time to the firmware upload service, the firmware is up to 99%. The firmware is already sent to the fitness tracker. Now what happens is, it's waiting for you to send the checksum. Now you would say to the fitness tracker saying that, hey, I'm sending the checksum, that is by initiating with a 04 byte. So now you have a checksum. So now if the checksum is matched with the receiver as well, it is going to straight accept the firmware. So this is how exactly it's working. At the end, if the firmware is being sent, you could just send 05 to reboot the firmware, to reboot the fitness tracker. And once I uploaded the firmware, this is what I could do. I could change the device name from something, from some vendor to the Jasper. Jasper is my dog, by the way. So I could change the device name to something else. And then if you see there is something, this is just a proof of concept, right? So I could change the software revision number to version number 9.9.9. Now the funny thing is that this fitness tracker is never going to connect to its central mobile application. It's because what happens is, it's right now running on the version 9.9.9.9. But the fitness tracker mobile application has the version number, example 1.2.3, and it's going to think that there is already a latest software running on the fitness tracker, and I don't have to upload, and I don't have to connect, and I don't have ability to connect. So once you change this device name and software revision string, you could never connect that particular fitness tracker to the mobile application, to the central mobile application. And what about the skull icon? Yeah, this is what exactly I was able to do by uploading the form, by changing the firmware and then reverse engineering the resources file. Again, this is just a proof of concept, but you could do a lot of things. You could exploit much more than this. Firmware update over the year is actually a really cool feature that is found nearly on all the embedded devices. I demonstrated this how this feature could be exploited to allow attackers to inject malicious firmware modification to embedded devices. The problem here is that hardware manufacturers do not cryptographically sign the firmwares for these small devices. So what happens is, at any point in time, this fitness tracker will accept firmware from anybody. That doesn't matter if that is from the particular vendor or maybe any attacker that has actually injected particular firmware. So you don't have to physically toss that fitness tracker to upload that. You could just sit here and send the firmware to anybody's fitness tracker. It's just going to accept that. If the solution for this could be cryptographically signing the firmware. Again, same answer. If they do all this sort of security stuff, the cost of the devices is the main issue, right? Yeah. So I'm at the end of my talk. So does anybody has any questions for me? If this tool is available there in the GitHub, maybe you could just download that. This tool is readily available. If you wanted to prank your friends or maybe anybody, and if you wanted to hack any fitness tracker in your vicinity, this tool is there in the GitHub as well. Yeah, this particular, the one I did was for MFBAN. You could change some other, you could change the characteristics actually. It's just that characteristics is different, right? So you could change the characteristic and you could do the same thing on any other fitness trackers as well. Any other questions? Yeah.
Did you get in touch with the manufacturers of this device to inform them about the possibility?
Yeah, I got in touch with the device manufacturer. I got in touch with them, but the problem is that they just don't want to implement that because of the device cost issues, right? This is the problem with the BLE stack, where you could snip the packets, right? Yes, I was in touch with the manufacturers. So thank you for joining me here. Thank you.